Hi there. In this video, we're going to be going through the arrays section of the deep dive. We're going to be going through the difference between the native array and the Ivy array, explain a little bit about why we have this distinction, what the benefit of having an Ivy specific array class is, and why this is something that is necessary, and just kind of go through everything related to the arrays in Ivy. Okay, so let's get started. First of all, it would be good to get the docs open. Perhaps could have done this already. Okay, so docs. And we're going through the arrays section of the deep dive, so it's here. Okay, so firstly, there are two types of arrays in Ivy. There is the native array, and there is also the Ivy array. The native array is quite simple to explain. Basically, the native array is simply a placeholder class for a backend specific array. So this is, for example, a NumPy ND array, a TF tensor, or a torch tensor, etc. And at the beginning, we initialize this as an empty class. So basically, if we look here, we can see that it's just initialized like this. It's just kind of a dummy class. And then what happens is, when a framework is set, then we overwrite this, this dummy class with the actual framework-specific class, as shown here. So what then happens is that in the case of a PyTorch backend, we then overwrite this native array class with torch tensor, and this happens basically during the framework setting, which is explained in another video. But basically, we go through everything in the global Ivy dictionary and replace it if it is also defined in the backend specific subfolder. So in this case, we're going through everything in the torch folder that's been imported. So this native array is something that is located in the torch folder. It's also located in the Ivy folder, and therefore this is overwritten with this, basically. And this is happening in the framework setting logic, which is explained in another video. Okay, so that's that. And also another quick point on the reason why we define this initially. Partly it's because this is necessary in order for us to be able to overwrite it. We need it defined in the Ivy array in order to overwrite it with the backend specific version. But also it's necessary for type hints, because for many functions we return, for many functions we accept a union of Ivy array and native array instances. And in order to be able to write this type hint, we need to have the native array defined somehow. And in the order of importing, we first import all of this stuff, and then we start importing all the modules further down. And therefore, it needs to be defined first such that these modules can have the type hint. So yeah, that's another reason why it's defined here, right at the top of the init file for Ivy. Okay, so that's the native array. Pretty straightforward. So now the Ivy array. And basically, the Ivy array is a simple wrapper class which wraps around the native array and stores it in the self data private attribute. So the self.data attribute here, basically we initialize the Ivy array with data as an input. And if data is already an Ivy array, we store what is actually the native array here in the data attribute. Likewise, if it's a native array itself, we store it here. So basically, the Ivy array wraps a native array in this attribute. And yeah, you might ask, why have an Ivy array class at all? Why do we not just use the native array classes? Well, this is for a few reasons, and we'll go through them one at a time. So the first point is that we are able to have a lot of instance methods implemented on the Ivy array, which can actually just make things a lot simpler and more readable when coding. So there's actually a pretty good example of this here. So if we go into the design section, if we go into Ivy as, is it building blocks? No, Ivy is a framework. We go to Ivy array. We do show a couple of examples which show the benefit of instance methods in general. And this is a slightly exaggerated example, but it certainly illustrates the point. So without the Ivy array, if we wanted to do a lot of complicated reshaping, like reshape and flip and transpose and reshape again, if we had a lot of stuff like this to do, then we end up kind of having each of the functions on the left-hand side and each of the arguments branching out on the right-hand side. And you can end up getting bits of code like this, where it's very hard to intuitively see which arguments are applying to which function, because we kind of have the outermost arguments going with the innermost function and so on. Particularly if the first argument in these functions is the array, which is very often the case for like element-wise functions and manipulation functions, and many array functions essentially consume the array in argument 1 and have everything else in the subsequent arguments. And in this case, you end up getting this really kind of, each function and its arguments get further and further out if you do lots of things in line, in single lines of code. The alternative will be to just have 4 lines of code here, but sometimes you don't want to do that. Whereas with instance method, you can actually, particularly for functions which consume a single array, you can essentially group the function name and all of those arguments together like this. So this would do the same thing. We'd have reshape here, dot transpose, dot flip, dot reshape, and it's just much easier to see what we're reshaping to, what we're transposing, and what we're flipping, etc. So anyway, this is kind of an exaggerated example advocating for the benefit of instance methods on arrays in general. And this is something we want to leverage in Ivy as well, which is one good reason for the Ivy array class. Okay, so hopefully that was giving good motivation on that front. So a quick point here, again, is that given that we then decide to have so many instance methods in Ivy and we want things to be organized, we essentially group these instance methods into topic-specific parent classes, which follow the same groupings as the submodules do in the functional API. So what you'll see here is, a quick point before that actually is just that in general, every single function in Ivy which accepts at least one array argument in the input, each of these functions is implemented as an instance method on the array. So we have quite a lot of instance methods, and anything that fits this template is added. Apart from a couple, so actually the exception is nest functions, which can accept kind of anything in the input. They essentially do arbitrary nesting of functions across arbitrary nested structures. So they can contain arrays, but they don't need to, and these are not added as instance methods. And likewise, the meta module is not added. These are kind of slightly higher level functions about meta learning and are not really in keeping with what makes sense to be added as an instance method on an array, because they're doing much more than manipulating arrays or something like this. Okay, so these are the only 2 exceptions really. And yeah, as we just said, the organization of the instance methods follows the same structure. So it follows the same structure as the functional API. So here we can see that the array class inherits from a load of parent classes, each of which have specific instance methods implemented. So I think the example we show is array with element-wise. And what you'll see is that this is an abstract class, so this is not supposed to be instantiated in isolation. It's kind of essentially, the sole purpose is to group things in an intuitive way for the Ivy array, and therefore we shouldn't be instantiating this on its own, thus this. And we have all the element-wise functions here. And the same is true for other parent classes, which the array inherits from. Okay. So that's that. So yeah, each instance method simply calls the functional API function internally, but passes in self.data as the first array argument. And a good example of this is Ivy add. So let's open that up. And you can see here that, of course, self is the array self. This can be, we'll explain this a bit more in a moment, but this can be a native array or an Ivy array. And then we just call the functional API function internally, but hard code the first array argument being self. And this is the same with all other functions as well. Okay, one point to make here is that it is not necessarily the first argument of the function, it is the first array argument of the function. So one quick example of this is that the concat function doesn't take an array in the first argument. It takes a list of arrays. So we would then essentially pass a list with self being the first item in that list and so on. So just important to mention that self.data replaces the first array argument in the function. Okay, so another one is that we also do not set the out argument to self for instance methods. And also, if the only array argument in a function is the out argument, then we do not implement this instance method. For example, we don't have an instance method for ivy.zeros, which doesn't actually consume an array apart from the out argument. But the reason for this is that basically the out argument isn't really like a function input in a normal sense. It's essentially a placeholder for the output. So it's essentially the location in which the result will be written to in memory. So it doesn't really fit the same profile, and therefore we don't add instance methods just because it has an out argument. Okay, so that's that. Yeah, and then given that we've just gone through a relatively simple set of rules which underpin when to add an instance method and exactly how it should be added, just replacing the first array argument with self.data, we could actually write a script to implement all of these instance methods for us. And that's actually exactly what we've done. As a fallback for the source code implementations in case they're not added for any reason. So basically here, we call add ivy array instance methods. We pass in the array class and all of the submodules, and then we basically go through each of the modules. We go through each of the key value pairs in the dictionary of the module, and if the value is an executable function which is not already implemented, then we set the attribute with the function name, and then set the value of this attribute to be the newly wrapped function, which is defined here. And to quickly go through this, basically what we do is we first get the function name, so this will be the functional API version of the function. We then have this array spec, which basically says the indices of all the arrays in the function. So this will give us where kind of the index, which enables us to set the first array element in the arguments. And then basically we basically just insert self.data into the arguments in the appropriate place, provided that it is actually belonging in the arguments in the manner in which it's being called right now. Otherwise, if it is not actually in the arguments, then we replace it in the keyword arguments instead. Yeah, anyway, so this basically just programmatically does what we just described, so that we actually have every instance method added. But we don't rely on this entirely. What we could do is just say, let's not add any instance methods. Let's not have all of these array with element-wise classes and all this kind of stuff. Let's just have a really simple array class and just add everything programmatically. And this actually works. We've tried this, and every instance method is added exactly correctly at import time dynamically. The only downside of this is that code shouldn't only work, it should also be as intuitive as possible and as readable as possible. And when stepping through code, the more that you can be stepping through kind of independent, documented functions, and the less you can be stepping through kind of very abstract, I don't mean abstract in the literal sense, but very kind of conceptually general functions like this, where there's just a general args that are being captured, keywords args captured, a very general doc string, and you're kind of stepping through code like this all the time, then it becomes very hard to kind of work out what's going on. And it's much nicer if when you call an instance method on an array, you're not entered into this kind of general wrapper function, but you're actually entered into, you actually kind of step inside an actual instance method where you can then clearly see what's going on. So this is really the only reason, the only motivation for an explicit source code implementation, because it makes things just much more intuitive for developers. It also has the benefit that IDE completions, auto-completions will work as well. Anything that's only dynamically added is essentially kind of invisible to anything that passes the source code and gives you helpers to kind of auto-complete the function name and stuff. So there's lots of benefits to having explicit source code implementations. Even though it's just a lot of manual work to implement them, once it's done and it's much more clear. Okay, so that's that. Awesome, so what next? So yeah, literally what we just said, why source code implementations are good and why we are adding them. Yeah, so now we can talk about the special methods. And just in case you're not sure, special methods are basically methods which begin and end with a double underscore. They are very common for operators, so for add and subtract and multiply and divide, but also they're used for like setting items in a class and various other things. Also the representation when you print them and a whole host of other things. And basically all of the special methods which deal with operators, and by that I mean, for example, when you do x plus y, what that does under the hood, as far as Python is concerned, is it calls x dot add y, and this is effectively what happens under the hood. If that doesn't work, it will then call y dot radd x, which is like reverse add, and it will just use the other instance method if there isn't one on x, or it doesn't work. But this is effectively what these do. And this is just making the point that in the ivy array, pretty much what we do is just call the ivy.add function, again with self.data and other. So we explicitly control each of these operators to just call the ivy functional API equivalent of the operation. Okay, yeah, and this is also in accordance and in adherence to the array API standard, which basically says the same, which is that all arrays should basically call the corresponding function when an operation is performed. Yeah, okay, but there is an important difference here, which is that for most, like these, it's pretty simple. We just call, the corresponding function. For some, there are differences, and this actually alludes to another important reason for the array, because if we had, yeah, and this is actually explained a bit more here, but I can explain it now as well. If we had no ivy array class, we would have no control over the operators. And as an example, when we try to do something like set an item, such as, we have an array x, and then we do x, 0 equals whatever, and we kind of try to set part of the array. For frameworks which have immutable arrays, such as JAX and TensorFlow, this would throw an error because, and this is for good reason, because JAX and TensorFlow have the design such that the arrays are only defining a kind of piece of a computation graph, which then is part of a computation to another tensor and so on. So the idea of like updating the memory in place for a tensor doesn't make sense in that paradigm because it's part of a computational flow from inputs to outputs in kind of a functional manner. So in-place updates don't make sense. However, for other frameworks such as NumPy and PyTorch, they do support in-place updates, and you can kind of juggle around the memory of a tensor all you want. We want to be able to support in-place updates as far as Ivy code is concerned, and therefore we need to have special consideration given accounting for whether the backend supports it or not. So if we can actually call the corresponding special method on the native array, which will be a Torch tensor, a NumPy array, whatever, if we can call this, then great, we'll just delegate to the backend. However, for JAX and TensorFlow and any others which do not support in-place updates, then we need to kind of mimic this in-place update by performing a scatter operation into a new tensor, and then keeping this stored in the self.data. So as far as the Ivy array is concerned, it is an in-place update because the ID, when you call Python's ID function of Ivy's array class, it would be the same ID because it's the same instance. But under the hood, it will be a new native array that's being wrapped, basically. So this is kind of a clear example of where we need to have some slightly different behavior depending on the backend. Okay, so that's that. Yeah, okay, so now we can go on to array handling. So when calling backend specific functions such as torch sign, we must pass in a native array. and this is not surprising, for example, torch.sign will throw an error if we try to pass in an Ivy array instance, because it doesn't expect to have anything other than a torch tensor in the input. So yeah, and this is also reflected in the backend type hints of our backend functions. So we actually also say in the backend, by the time we come here, X needs to be a torch tensor provided as an input. Yeah, but however, all Ivy functions must return Ivy array instances, which is reflected in the kind of type hints here for the corresponding function in the Ivy subfolder. And we must be returning here an Ivy array. And again, this leads to the point that the reason that we need to always return an Ivy array from every Ivy function is so that we can guarantee that the code following that function remains framework agnostic. And again, we can't do that unless we have control over the setItem special method, for example. If we just did ivy.sign and we've returned a native array and then we try to set item, this will depend on the backend, and therefore the whole kind of framework agnostic approach breaks down. So this is why it's necessary to return an Ivy array. And likewise, I'll just extend on that a little bit just to say that set item is an extreme example, but the same is the case for add or anything, even the very simple ones. It might be the case that they all are consistent, but as we support more backends, different frameworks have different broadcasting rules with regards to shapes and data types. So it might be the case that for one backend, adding a float32 and a float64 array gives a float64, and in others it would be a float32. I mean, in that case, I would be pretty confident that all of them would up broadcast. But there are cases where adding an integer and a bool together, some would raise an exception, some would automatically cast the type. So even as simple as addition, we can't necessarily guarantee uniform behavior. It's the same with shapes. Maybe some frameworks say, no, these arrays must be identical shapes in order to add them element-wise, and others might say, actually, no, we can add things with different shapes, so long as the shapes are broadcastable and we can kind of, make intuitive sense of what the final shape should look like. So any operators really can have non-consistent behavior, and therefore our only hope to actually control this is to wrap things into an Ivy array where we can actually enforce consistent behavior in these special methods. So that's why we need to return Ivy arrays, but we also need to pass in native arrays in the backend. And this brings us to the requirement for us to effectively continually wrap and unwrap each Ivy function when we call it. We need to accept Ivy arrays in the input. We then need to make sure we convert any Ivy arrays in the input to native arrays. We need to call the backend function, and then we need to get the returned native arrays and make sure we convert all of those back to Ivy arrays. And we need to do this for every single function in Ivy. And a final point here, which is explaining why we have a union over a native array and an Ivy array. But actually, let me just quickly make sure I'm following through the right logic. It'd be better to follow the text as much as possible. So, so we've made this point already. All Ivy functions must return these. The reason for this is because we need to make sure it's agnostic, as we've just said. For example, these operators, we need them to be called on the Ivy array class so that we have control. For most cases, it wouldn't be a problem on the native array class, but again, for some like setItem, there's big differences which must be addressed. Given all Ivy functions return Ivy array instances, all Ivy functions also support. Yeah, exactly. So this is why we need to be able to. This is why we need to be able to accept Ivy array instances in the input, because we need to return them as well. So to chain Ivy functions together, we need to be able to support Ivy array in the input. And again, so this is the pipeline then that makes this work. So as I just said, all Ivy array instances in the input are first converted to native array instances. We then call the backend specific function, such as torch.sign, passing in the native array. Then we convert all of the native arrays back to Ivy arrays in return. And this is the general pipeline. Given the repeating nature of these steps, this is all entirely handled in the inputs to native arrays and the outputs to Ivy arrays wrappers, which is explained in more detail in the function wrapping section. And I won't go into crazy detail, but basically what we do is we have a function where we take all of the arguments, all the keyword arguments. We have this helper called args to native, which will do this for us and basically recursively search and convert all Ivy arrays to native arrays. And then we pass these into the function. And likewise, I mean, the other one is outputs to Ivy arrays, which is pretty much the same. We have this toIvy helper function. Again, we do it in a nested manner, which means we traverse tuples and lists and any kind of nested structure and convert everything back. Okay, so that's that. And again, this is explained in more detail in the function wrapping section. Okay, we're getting close. So, and the next point is that we also accept native array instances in the input. And this is for a couple of reasons. Firstly, I mean, yeah, we must convert to native array instances anyway, so it kind of makes sense to just support them because this is where we're going with the input arrays anyway. And also it just makes it easier for you to kind of combine framework-specific code with Ivy code. It makes sense that you can just do a load of torch operations on some torch tensors and then jump straight into some Ivy code without needing to say, oh, okay, now we need to convert all of our torch tensors into Ivy arrays by wrapping them explicitly. So we just say, no, you can just pass in native arrays straight into any Ivy function and it will then be kind of wrapping it from Ivy from that point forward automatically. Yeah, so hopefully that makes sense. Okay, so yeah, the exception to this rule is that native array instances are not permitted for the out argument. And again, this is because the out argument effectively dictates where the result should be written to. So it needs to be the same type as the output, and the output must be an Ivy array. Therefore, the out argument must be an Ivy array if specified. This is all explained in more detail in the in-place update section as well. Okay, so as a final point, a bit of extra attention is actually required for the compositional functions, and the reason being that these don't directly defer to a backend implementation. And if, for example, the first line of code in a compositional function performs operations on the input array by kind of, x plus y or something like this via an operator, then this will call the special methods on the native array directly, and not on an Ivy array, which is what we require to guarantee uniform behavior. And this will be a problem. Therefore, all compositional functions, not all of them actually, all compositional functions which start with an operator on the first line, which is actually none at the time of recording, but it's something that we have written in to make sure that we understand why this will be necessary as and when it arises. Because all Ivy functions should accept native arrays in the input, and because compositional functions don't just dive straight into a backend implementation, we want to avoid the problematic case where we perform an operator on the first line, which then is inconsistent between frameworks, and therefore we have another helper which is called inputs to Ivy arrays, which effectively will make sure that all of the inputs to the function, all the native arrays are converted to Ivy arrays before calling the function. Okay, so that's that. And that is everything really. So that's the last point. So this has been quite I'm sorry if it's a bit slow. I try to be very thorough and very clear, but perhaps at the danger of repeating myself a little bit. But hopefully that's clarified the native array, the Ivy array, how we handle arrays with the decorator, why we have a union type hint in the inputs of functions and just the Ivy array in the output of functions. And then the last point is just if anyone has any questions about this, we do have a dedicated kind of discussion on this on the GitHub, which anyone can continue to contribute to. We have a dedicated channel for this on the Discord, and of course there's also the comments on this video. So lots of places for you to ask questions and get involved if there's anything you'd like to inquire about further with regards to this video. But yeah, I think I'll end it there. Thank you very much for watching, and I will see you in the next video. Bye for now.